Okay, starting out with section 4.4 and 4.5. This is about related rates. Now, what related rates are is that they are two variables that are growing together or at different rates. And so you're going to be solving a lot of questions where it says, find this rate at this point in time. To review, we're going to use implicit differentiation. Now remember, when you differentiate this, notice how that the x's and y's are mixed in together. And so we want to find its derivative. And just to remind you guys, when you take a derivative of y, it turns into dy dx. And so I already completed this problem. We're going to take the derivative of each side. And so when it distributes through, you're going to get the derivative of x squared, which is 2x. You're going to get the derivative of 2y, which is just 2. But since we took the derivative of y, we have to write dy dx. And so we got minus 2 dy dx. And when we take the derivative of 5x, you just get 5 equals, when you take the derivative of y cubed, the 3 comes down out front, turns into 3y, and then subtract 1 from the 3 to get 2. So it's 3y squared. But since we took the derivative of y, you have to write it as dy dx by the chain rule. And then minus the derivative of any constant is 0. So if we were trying to find its derivative, we need to isolate this dy dx. So what I did is I added 2 dy dx to each side. So you just basically move it over here by adding it. It disappears from this side. And then you just get your plus 2 dy dx. From here, we have isolated the dy dx's. So we're going to factor these out of these terms, which is here. Because again, if I distribute, 3y squared dy dx is right here. And then plus 2 dy dx. And then after this, you just divide by 3y squared plus 2 on each side. And we get our final answer here. So we're going to do this implicit differentiation, but we're going to do it with respect to time. You can differentiate to any variable. You just need to put the appropriate dy dx, dy dt, whatever you're trying to do. So because these are related rates, they're going to be related to time. So we're going to do the same thing. We're going to take the derivative with respect to t. So from here, if we just take the derivative of y, that's 1. But since we took the derivative of y with respect to t, we had to put dy dt. Now, I'm going to show this once, and then we're going to do a shortcut and not write it the same way each time. But here, when we do the right side, so we're going to take the derivative here. So 3 comes down, multiplies, that turns into a 6. And then we're going to subtract 1 from the 3. So that's going to be 6x squared. And since we took with respect x and t, it's going to be dx dt. And then when we take the derivative of minus 4x, the x disappears. It just turns into minus 4. But since we're taking the derivative with respect to time, it is dx dt. And then finally, when we take the derivative of a constant, it's 0. And then that's all it's asking us to do. And then we're going to factor out these two terms outside. So starting out, we just get dy dt. And then when we factor out this, we're going to be left with 6x squared minus 4 inside the parentheses. And there you go. There is our final answer. Now, when I do the next ones, I'm not going to write each of these because it's going to get a lot. So I'm just going to put it on the outside. But this is what's happening so we can see it. All right, moving on to question 2. We're going to take the derivative of each side. So again, when we take the derivative of 5p, that is just 5. But this is going to be dp dt because we took the derivative of p with respect to t. Now, again, so let's take the derivative of q now, of q squared, sorry. So that's going to be 2q. And again, there is supposed to be a dq dt here, but there's also going to be one here, and then we're just going to factor it out at the end. Take the derivative of negative sine, and that's going to be negative cosine. But again, there's supposed to be a dq dt here, but we're not writing it. And then finally, take the derivative of e to the power of 3q, which doesn't change it, but then the chain rule means we'll have to take the derivative of 3q. So just to review, the derivative of 2q, or of q squared, is 2q. The derivative of sine is cosine. And the derivative of 3eq is 3eq. But with the chain rule, we have to take the derivative of 3q, which is q. And again, each of these terms has a dq dt attached, but we're just factoring it out to the outside, and we'll write it out here because we have to do that anyway. And it just saves a lot of steps, but there is example 2. Oh, I am so sorry. Just to review the problem, it does say take the derivative with respect to z. So this is supposed to be dz. It's weird to say. So there you go. Oops, that was a little minor mistake on my part. Now, example 3, this is where we're going to really get into the calculus and the applied problems. So notice how it says find the derivative of y with respect to t in terms of y of x, and it gives us it tells us dx dt is 4. So whenever we get this rate, we can substitute 4 in for it. Okay, so I will show all the steps on this one. So the derivative of x squared is 2x, and the derivative of y cubed is 3y squared. And again, this is going to be dx dt because it's with respect to x. And this one was going to be dy dt. And then on the right side, the derivative of any constant is 0. Okay, so now this question is asking us to solve for dy dt. So we're going to solve for this variable. And remember, we have that this one equals 4, so we can make that substitution. Okay, now solving, we are going to move this over because it's already subtracted, right? So we're just going to add this over to the other side. And 2x times 4 is 8x. And then finally, our last step is to solve for dy dt by dividing by 3y squared on each side. And there you go. There is dy dt. Okay, so this is going to be the last example of this type before we actually start doing related rates problems. All right, again, so the derivative of log is going to be 1 over the inside. And then the chain rule says we have to take the derivative of the inside as well. The derivative of the inside will be 6x and then plus 4. And we need because again, we're taking the derivative of x with respect to t. So this is going to be dx dt on the outside. Now on the right, we're going to take the derivative of cosine, which is negative sine. But also we have to take the derivative of the inside, so we're going to get a chain rule of 2. And since we took the derivative of y with respect to t, this is going to be dy dt. Okay, so this looks complicated. It's not going to be too bad because, again, we're trying to solve for this. So we're basically just going to divide this out, but we will clean up the right side and look over here where it says dx dt is -3. So that value is going to be -3. So if I clean up the left side, it's going to be -3 times 6x plus 4, all divided by 3x squared plus 4. Because again, this is -3, which is on the top, and then that goes up here to the 1, equals -2 sine of 2y dy dt. And then finally, I'm going to divide this to each side. Now, when you divide it, it's just going to go down here with this one. And I guess the best way to think of this is think about it as multiplying, and it's a little bit easier as 1 over -2 sine yada yada yada. Those cancel out. And then when I do it over here, right, this will combine with the bottom. So my final answer, well, not really my final answer, but the second to last step is here. So here is my derivative. Oh, and I did make a mistake. This is supposed to be dy dt, not dy dx. So here is my final dy dt. Now I could clean this up a little bit more. I can cancel out these negatives. I can distribute the 3 through. Question 5. The circle above is expanding and contracting. Okay, so it says find an expression for the rate that the area is changing with respect to time. So whenever you see find an expression and it's about rate with time, you're going to take the derivative with respect to time. And just in case you don't know, there is the area of a circle again. Okay, so if I take this derivative, the derivative of a is just 1. But since it's the derivative of area with respect to time, we're going to call it dA dt. And then on the right side, remember pi is just a variable. I'm sorry, it's just a constant. It's a number. So we just kind of ignore it. And we're going to take the derivative of r squared. It's going to come out, multiply outside, and then subtract 1. So this is going to be 2 pi r. And again, since we're the radius is the variable, we're going to call this dr dt. And there's our expression. Okay, part B. The radius of a circle is increasing at a rate of 4 centimeters a second. I'm going to highlight that in green. At what rate is the area of the circle increasing with respect to time when the radius is 7? So if you notice here with our equation, the 2 and the pi are just constants. There's this variable, there's this rate, and then there's this rate. Now, this is the rate that the area is changing with respect to time, and this is the rate that the radius is changing with respect to time. So if we look up here, and when you say the radius of a circle is increasing at a rate of 4 centimeters per second, that is what this rate is. That's dr dt, because it's the radius changing with respect to time. So we have dr dt equals 4. It's positive because it's increasing. And then we have what the radius is. We have r equals 7. And just to be sure, it says at what rate is the area of the circle changing with respect to time. So we're trying to find dA dt. That's what we're trying to find. So all we have to do is plug in these values and say dA dt is going to be 2 pi. The radius is 7, and dr dt is 4. And we get that this equals 56 pi. And then we do need units. These don't have units with them. This is in centimeters, and this is in centimeters per second. So our units are going to be centimeters squared per second. Because again, this is in centimeters, and this is in centimeters per second. And so there is our area, and it's an area, right? So area is about squares, about units squared. But it's a rate, so it's per second. All right, part C. The area of a circle is decreasing at a rate of 10 centimeters per second. Centimeters squared per second, sorry. At what rate is the radius of the circle changing when the radius is 3? So we know that r is equal to 3. Now, this rate, this is going to be dA dt, because it's the area of the circle is decreasing, which is negative, at 10 centimeters per second. And then we are finding how fast the radius is changing. So we're looking for dr dt. That's what we're looking for. So plugging in all the values, we have negative 10 equals 2 times pi times 3. And then again, dr dt is what we were trying to find. And then all we have to do is divide out the 2 pi times 3 on each side. And 2 pi times 3 is 6 pi. So there is our answer. We just need to figure out what the rate is. So let's think about this. This is going to be in 3 centimeters. And this is centimeters squared per second. So we have centimeters squared per second. And then we are dividing by 3 centimeters. So there's going to be another centimeter on bottom, which is going to cancel out. So our units are in centimeters per second. And again, the rate, of a radius is in centimeters over time per second. So there's question 5. When you do related rates problems, here's kind of a step-by-step guide on how to do it. When we talk about static variables, those are variables that don't change, that are fixed. So like here, static variable would be 3, right? The rates are all dynamic variables. So just some tips and tricks. Always draw a picture if you can. Label it with the static variables only and use arrows. And you'll see that in the next example. Be careful if it's decreasing, that's a negative value. Always look at units. There is going to be an equation you have to use at some point. So knowing your areas of circles, spheres, the surface area of spheres, most of the time that will be given to you if it's kind of complicated, but you're expected to know basic formulas like the area of a circle. You're always going to differentiate with respect to time and then solve for your desired value. All right, so here's all the things, all the parts here. So a 12-foot ladder is leaning against a wall when it begins to slide down at a rate of 2 feet per second. At what rate is the base of the ladder moving away from the wall when it's 5 feet from the wall? So let's draw a picture first. So that's going to be the wall. And this thing right here is the ladder. Okay, so let's label it appropriate. It's 12-foot ladder, so that's 12 feet. It's leaning to go on, begins to slide down at a rate of 2 feet per second. We're not going to write that on our picture because that's a rate that we plug in. And at what rate is the base of the ladder when we're 5 feet from the wall? So let's say this is my y value. We are going down. This is my x value. And the ladder is moving this way. So there, I think that's a good enough picture. So let's translate the information from the problem. So we know x is going to be equal to 5. Because again, it says when we're 5 feet away from the wall. So this point right here is going to be 5. Now, this rate right here, since it is decreasing on the y value, this is going to be dy dt is going to be -2. and that's going to be feet per second. And what are we looking for? So we have y, we have x, or we don't have y, we have x, we have dy dt, and it says at what rate is the base of the ladder moving? So we want to know, we're trying to solve how fast it's moving this way to the right. And that is going to be dx dt. That's what we're trying to find. Then the base of the ladder is the x direction. Okay, so now that we have all that, we need to write an equation that kind of glues all this together. And we have a triangle here. We know this is y, x, and 12, so we can write an equation using Pythagorean theorem. X squared plus y squared equals 12 squared. Okay, so now we need to take the derivative. So, and again, we're taking a derivative with respect to time. So we're going to have 2x, and again, that's going to be dx dt, plus 2y, and that's going to be dy dt. And then the derivative of 144 is 0. And again, we have almost everything we need. We are trying to find dx dt. So this is what we're trying to find. We know that dy dt is -2. We have that x is equal to 5. So the only thing that we're missing from our question is y. And we can go back and solve y. Because we know x is 5, we have an equation, so we can solve for y here. So if I sub 5 in there, I get 25. All I have to do is subtract 25 from each side, which gives me 119. And then if I square root, I have that y is equal to 119. So now I have everything I need. I'm trying to solve for the green dx dt, and I have all the other values. So we're going to have 2x, which is 5. Dx dt is what we're solving for, plus 2. Y is going to be the square root of 119 times -2 equals 0. So this is going to be -4. I'm going to, because again, this all turns into -4 times root 119. After that, I'm going to add this to each side and then divide by 10. So my final answer is going to be dx dt is going to be equal to 4 times the square root of 119 over 10. And we need to know the units. The units are going to be in foot, I think it's feet. Yeah, so we're in feet per second. And again, I always do this. That is dx dt. And there you go. So there's example 6. So we're going to do this 2 more times. So we're doing area of a circle. So just to remind you, area of a circle is pi r squared. And we did the derivative. We had that dA dt was going to be 2 pi r, and that's dr dt. All right, but it says the area of a circle is increasing at a rate of 5 inches per second squared, or 5 square inches per second. Find the rate of the radius of the circle is changing when the area is 36 pi inches squared. So let's draw a picture. Okay, so there's the picture. It is increasing and expanding. Not too helpful in this case, but it's always a good idea to do it. Translate the information that we have. So we have that the area of the circle is increasing at a rate. So we have dA dt is going to be 5. What are we looking for? Find the rate of the radius. So the rate of the radius is going to be dr dt. That's what we're looking for. And it does tell us that at some point in time, we are going to be at 36 pi inches squared. Okay, so again, area of a circle is pi r squared. The derivative we already did before. So let's look what we have. We have this variable. We do not have the radius, and this is what we're trying to find, is the dr dt. So we need to solve for the radius, and that's where this comes in. So we can say, we know what the radius is if we know the area. So this is going to be 36 inches squared. Oops, 36 pi inches squared. I'm not going to even write the units. This is pi times r squared. So if I divide by pi, I get 36 is the radius squared. So we're going to get that the radius is 6. We're going to use positive 6, not negative 6. So that is all of our values. So what is dA dt? That is equal to 5. Our radius was equal to 6. And we are trying to find dr dt. So this is all going to be 12 pi, and then we're going to divide it. And then there you go. So what are our units? Well, okay. What was area? Area was inches squared per second. 2 has no variable or units. Pi has no units. R has inches. So it looks like the rate has to be inches per second. And there you go. There is number 7. Last question, 8. So this is just one question. Water is being poured into a cylindrical container at a rate of 4 cubic meters per second. The radius of the jar is 3 meters. At what rate is the height of the water changing when the water is at a height of 10 meters? So let's draw a picture. So there's my picture. We do know that the radius is 3. And we are looking for the height of the water, the height. So this is our variable here. Okay, we need to know what the volume is of a cylinder. If you recall, it's base times height. The base actually is a circle. Sorry, it's a cylinder. So the base is a circle. So it's going to be pi r squared h. That's the volume of a cylinder. We know we're going to have to take its derivative with respect to time. Okay, so after we have the volume, let's see what values and units we are given. It does say water is being poured into some cylindrical container at 4 cubic meters a second. So that's how cubic meters per second is a volume rate. So that is dV dt. How can I tell that, guys? Because it's cubic meters. Cubic meters are our volume. We're given that the radius of the jar is 3 meters. And we are looking for the rate of the height of the water. So we're looking for dH dt. Okay, so since we know that 3 is the radius, we can plug this in and say that this is 9 pi h. Again, because 3 squared is 9, and we know that the radius was 3. So let's take its derivative now. Okay, the derivative of volume is dV dt. And this is just going to be, again, the only variable here is h. Pi is not a variable. So this is going to be 9 pi. And then since I took a derivative of h, that's dH dt. And yeah, so just plug in what you know. We know that that's 4. and we're trying to find the other one. So this is going to be 4 cubic centimeters per second equals 9 pi dh dt. And then we're just going to divide by 9 pi. And again, think about it as multiplying by 1 over 9 pi. Those cancel. If I multiply by 1 over 9 pi, these go to the bottom. So it's going to be 4 over 9 pi. Now our units. So what are our units? So let's go back and check what we did. This 9 was, remember, the 3 squared. So this is going to be in centimeters squared. So we have 4. This is cubic centimeters, and then seconds are down here. This 9 was in centimeters squared. So we have, hold on, cubic centimeters per second. And then on bottom, the 9 was centimeters squared. So it looks like we're going to get centimeters per second. Oh, why am I saying centimeters? This is supposed to be meters. It's cubic meters. So same things apply, guys. This is meters. My units, I don't know why I'm thinking centimeters. It says centimeters, whatever. Anyway, that is it for related rates.